This video is about calculating heat of phase changes. And so at the end of the video, you should be able to calculate the effect of forces on the heat of fusion and vaporization of the substance, calculate the heat required for the substance to go through those phase changes, and determine the changes in energy of the substances. So when do we use Q equals M to delta T from our last video? And we can only use it if there is a delta T or a change in temperature, which means if we go back to our phase change diagrams, we can only use it on the solid only, the liquid only, or the gas only lines, which would kind of make sense if you also think of it in terms of specific heat. You can only use it if you're specifically talking about a solid, specifically a liquid, or specifically a gas, because there is going to be no specific heat for a solid and a liquid together. So the heat needed to change a substance from a solid to a liquid has to use another formula, and that is another formula on table T, noted as Q equals MHF, Q being heat, M being mass just like before, but HF being the heat of fusion. And going back to table B, the heat of fusion for water is 334 joules per gram. So every time you want to heat up water from a liquid to a solid, or solid to a liquid, you need to apply 334 if you're going to the liquid phase, and remove 334 if you're going to the solid phase. And so that is the first plateau, or the second line on your phase change diagram. Similarly, the formula looks very similar for heat of fusion, for heat of vaporization. So if you're changing it from a gas to a liquid or a liquid to a gas, you're going to be using Q equals MHV, again Q being heat, M being mass, but HV being the heat of vaporization, which is given as 2,260 joules for every gram. So if you have a gram of water and you want to vaporize it, you have to put in 2,260 joules. And if you want to liquefy it, you have to take out 2,260 joules. So this might imply something about gases versus solids. It is much harder to make something a gas than it is to make it a solid, which is why that line was a little longer on our phase change diagram. The heat required to go from gas to liquid is a little bit more than it going from solid to liquid. So that's pretty important to note. The attractive forces between the particles are stronger in a solid than it is for a gas. So the solids easily just separate a little bit going from solid to liquid because there's still forces. But from liquid to gas, or its melting and boiling point, it's going to take a lot more energy because you need a lot more forces to break going from a liquid that has forces to none in a gas. So it takes more energy for going from a liquid to a gas, that should say, than a solid to a liquid, because you have to break all the forces of attraction. So moving on, we're going to try some examples. How many joules does it take to melt 16 grams of a sample at 0 degrees? So if you're talking about melting, you're at 0 degrees, you're going to have to use the MHF formula. So looking at the question, the mass was 16, and the HF of water is on your reference table as 334. And that means we're just multiplying across to get 5344. Now, if I'm talking about sig figs, I probably should only have 3 of them, so my final answer would be 5340 joules. We're going to do this one together. How much heat is needed to melt ice at 0 degrees if the sample weighs 255 grams? So again, identifying that you're melting at 0 degrees, so it has to be the MHF formula, and then you're just multiplying the HF on your reference table by 255, noting that you have 3 sig figs, so this number is just a little too many sig figs, so rounding it to 85,200 joules. You're going to do this next one. How much heat is needed to melt ice at 0 degrees if the sample weighs 134 grams? So take a moment to make sure your setup is correct, and you can check your answer. Again, identifying that it's melting at 0, so you're definitely using the MHF formula, multiplying the mass by how many joules you'll need, noticing your number has too many sig figs, and rounding it to only 3 since 3 were given, so 44,800 joules. Hopefully you got that one. We're also going to do some examples for heat of vaporization. So notice this question's different because it says it's boiling at 100 degrees. And so we're going to use the MHV formula, multiplying the mass by the HV formula's number 2260. Again, noting that you want to only have 3 sig figs in your answer since 250 grams was given with 3 sig figs. So together, a little bit slower, you have a 75.7 gram sample of water at 100 degrees. Again, that means vaporizing at 100 degrees. So your Q is unknown, but your mass was 75.7, and you're using HV because it's vaporizing. So you're going to set up your formula by multiplying your mass, 75.7, by your HV on your reference table B as 2260. When you multiply across, you get 171,000 joules. Note again, I make sure this has 3 sig figs, as does the mass that they were giving me, 75.7. Let's see if you can do it. How many joules does it take to boil 50 gram sample of water at 100 degrees Celsius? Once again, you're noticing that it says boiling at 100, so you're solving for a Q when the mass was 50 and your HV was 2260 because you're vaporizing. When you multiply the two numbers together, we got 113,000 joules, which, if on the side note, that could have been 113 kilojoules when you divide by 1,000. So it is important that you know that you can change joules to kilojoules at any moment if the question asks for it. Just a reminder that the vertical points were when temperature was increasing, so that's when your kinetic energy is increasing, and so therefore potential energy is constant, and you can use a Q equals mc delta T for any of those portions when your temperature is increasing. But what we're saying now is for the horizontal points, since the temperature is remaining the same, the kinetic energy is remaining the same, only the potential energy or phase energy is changing. In that case, you have to use the new formulas MHF for fusion and MHV for vaporization. This would also apply to cooling curves where your heat is removed. So again, the vertical points where your temperature and kinetic energy are decreasing, you can use mc delta T. But for your horizontal points, since they're the same as your horizontal points on the previous graph, your temperature is staying the same, you can't use mc delta T. You again have to use MHF or MHV depending on if you're freezing or if you're vaporizing it. So remember the 3 P's. If it's plateauing, is a phase change with potential energy, and those diagonal points are temperature changing, and therefore is kinetic energy or mc delta T. At this point, you should be able to determine the effects of IMFs on the heat of vaporization and fusion, calculate the heat required by a substance to go through a phase change, and determine the changes of energy of a substance.